For as long as we have looked to the stars, we have wondered if we are alone. We have scanned the skies for signals, for messages, for any sign that we are part of a larger galactic community. But in recent years, we have come to realize that the galaxy sends its messages in other ways, not through radio waves, but through physical messengers, silent travelers cast out from other star systems, journeying through the interstellar darkness for millions of years. In 2017, the first of these messengers, a strange rocky object named Oumuamua, tumbled through our solar system. In 2019, a second, more familiar-looking comet named 2I Borisov followed. And now in the summer of 2025, a third messenger has arrived. This is the story of that third visitor, a comet known as 3I Atlas. It is a story that is unfolding right now, written in the faint light captured by telescopes across the globe. Before we delve into the latest discoveries about this traveler from another star, I would love to know from which part of our world you are joining us. Let me know your city or country in the comments. And if you enjoy these calm explorations of our universe, consider subscribing to continue these journeys together. The discovery of a third interstellar object in less than a decade has transformed our understanding of the galaxy. It suggests that these visitors are far more common than we ever imagined, and that the space between the stars is filled with the wandering remnants of other solar systems. The arrival of 3I Atlas gives us our third precious opportunity to study a piece of another world up close. Its story begins on the 1st of July, 2025, at an observatory in Chile, where a routine sky survey detected a faint point of light moving in a way that defied explanation. The discovery was made by the Asteroid Terrestrial Impact Last Alert System, a network of telescopes known as ATLAS, whose primary mission is to scan the sky for asteroids that might pose a threat to Earth. On that July night, the telescope in Rio Hurtado, Chile, captured images of a faint object moving through the constellation of Sagittarius. Initially, it was flagged like any other potential near-Earth object. But as astronomers around the world began to track it, a remarkable picture emerged. When they calculated its trajectory, it became clear this was no ordinary comet or asteroid. Its path was not a closed elliptical orbit around our Sun, but a dramatic, open-ended curve known as a hyperbolic orbit. This was the telltale sign. An orbit this extreme, with an eccentricity measured at approximately 6, meant the object possessed far too much energy to be gravitationally bound to our Sun. It was not a member of our solar system family. It was a tourist, just passing through. The International Astronomical Union's Minor Planet Center quickly confirmed the findings, and the object received its official designation, 3I Atlas. The 3I signifies that it is the third confirmed interstellar object, a worthy successor to 1I Oumuamua and 2I Borisov. The initial glimpse of this visitor was faint but tantalizing. At the time of its discovery, it was approximately 670 million kilometers from our Sun, well within the orbit of Jupiter. Almost immediately, astronomers noticed signs of activity. Unlike Oumuamua, which appeared as a static rocky point of light, 3I Atlas showed a faint, fuzzy atmosphere, a coma of gas and dust. This was a crucial clue. It meant the object had an icy nucleus, and as it approached the warmth of our Sun, that ice was beginning to sublimate, releasing gas and dust into space. It was not an asteroid, it was an active comet. The world's most powerful observatories turned their gaze towards the newcomer. The Hubble Space Telescope captured images in late July, revealing a distinct nucleus and giving astronomers their first rough estimates of its size. Somewhere between 0.5 kilometer and 5.5 kilometers in diameter. a perfectly normal size for a comet, but an extraordinary thing to measure for an object from another star. Its journey had brought it from the direction of our galaxy's core, a silent pilgrimage through the void that has now, by pure chance, intersected with our own small sunlit corner of the universe. With its cometary nature confirmed, and its interstellar origin proven, the real work began, to uncover the secrets that this third messenger has carried with it from its distant, unknown home. The initial detection of a faint, fuzzy object on a strange path is where the story of 3I Atlas begins, but the confirmation of its interstellar nature is where the true scientific detective work takes place. An extraordinary claim requires extraordinary evidence, and claiming an object has journeyed from another star system is one of the most extraordinary claims in modern astronomy. This confirmation is not a single event, but a meticulous process of observation, calculation, and the systematic elimination of any other possibility. For 3I Atlas, the evidence was unambiguous, centered on the unique geometry of its orbit. An object that belongs to our solar system, whether a planet, asteroid, or a comet from the distant Oort cloud, is gravitationally bound to our Sun. Its path is a closed loop, an ellipse. It is like a ball thrown into the air. It may travel a great distance, but it is ultimately destined to fall back. An interstellar visitor, however, is not bound by our Sun's gravity. It arrives with too much speed, too much energy of its own. Its path is an open curve, a hyperbola. It is less like a thrown ball and more like a bullet fired from an immense distance, passing through our cosmic neighborhood for a brief moment before continuing its journey back into the void, never to return. The shape of this orbital path is defined by a number called eccentricity. An eccentricity of 0 is a perfect circle. An eccentricity between 0 and 1 is an ellipse. An eccentricity of exactly 1 is a parabola, the precise line between being captured and escaping. For 3I Atlas, astronomers calculated an eccentricity of approximately 6. This number, so much greater than 1, was the definitive mathematical proof of its origin. It was moving far too fast to have ever been a member of our solar system. Even with this evidence, scientists rigorously tested other hypotheses. Could it be a native comet from our own Oort cloud that was somehow accelerated to this incredible speed? Perhaps a close encounter with a large planet like Jupiter, or the gravitational nudge from a passing star, could have flung it onto this extreme trajectory. Supercomputers were tasked with running these simulations, tracing the comet's path backwards in time. The results were conclusive. No plausible scenario involving the gravitational dynamics of our own solar system could account for the immense excess velocity that 3I Atlas possessed. It did not get a slingshot from within our system. It arrived already moving at a cruising speed of tens of kilometers per second relative to our Sun. By tracing its trajectory backwards into the deep past, astronomers could determine the direction from which it came, a point in the sky near the dense star fields of the constellation Sagittarius, towards the core of our Milky Way galaxy. The journey from its home star system, wherever that may be, was an impossibly long one. Even at its incredible speed, it would have spent millions, perhaps tens of millions of years, traversing the lonely, dark expanse between the stars. It is a fossil, a wandering piece of a world that may have formed long before our own. The confirmation of 3I Atlas as the third interstellar visitor is profoundly significant. When Oumuamua was discovered, it was a breathtaking anomaly, a 1-in-a-million catch. When 2I Borisov arrived, it suggested a pattern. The arrival of a third object in less than a decade solidifies a new and revolutionary understanding of our galaxy. It tells us that our solar system is not an isolated island. Instead, it is constantly moving through a galactic medium that is filled with the wandering debris of other star systems. The great emptiness between the stars is, in fact, littered with countless comets and asteroids, ejected from their own systems during the chaotic process of planet formation. We are just now, with survey telescopes like Atlas, becoming capable of spotting these tiny, fleeting messengers as they pass by. This realization opens up fascinating, if speculative, possibilities and gives new life to theories like panspermia, the idea that life itself could travel between worlds, sheltered within icy visitors just like this one. With the interstellar nature of 3I Atlas confirmed beyond doubt, the scientific community could now focus on the next great question: what is this messenger made of, and what secrets does it carry from its ancient and unknown home? With its interstellar origin confirmed, 3I Atlas became one of the most sought-after targets for astronomers worldwide. The brief window of its passage through our solar system represented a rare and precious opportunity. To study such an object is to hold a piece of another solar system in your hands, to analyze the raw ingredients from a world that formed around a different star. A global campaign of observation began, with telescopes of all sizes, both on the ground and in space, turning their attention to the faint, fast-moving point of light. These initial observations provided the first clues to its nature and presented a series of intriguing enigmas. The first task was to understand its basic physical properties. The Hubble Space Telescope, with its unparalleled sharp vision, played a crucial role. In a series of observations in late July and August of 2025, Hubble was able to resolve the comet's core, separating the light of its solid nucleus from the diffuse glow of its surrounding coma. These images allowed for the first reliable measurement of its size. The nucleus was found to be between 0.6 and 5.6 kilometers in diameter. This was a significant finding. It meant that 3I Atlas was not an unusually large or small object, but a fairly typical comet in terms of its size. The second interstellar visitor, 2I Borisov, had a similarly sized nucleus. This suggests that the processes that build comets in other star systems may produce objects of a comparable scale to those in our own. Hubble's images also revealed the comet's activity. A teardrop-shaped coma of dust was seen streaming from the nucleus, a clear sign that ice was sublimating, turning directly from a solid to a gas, as it was heated by the sun. This activity was a key difference from the first interstellar visitor, Oumuamua, which was entirely inert and appeared as a bare rock. 3I Atlas was behaving like a classic comet, which was both reassuring and scientifically valuable. While Oumuamua left us with more questions than answers, 3I Atlas offered a chance to perform a more direct, apples-to-apples comparison between a comet from our solar system and one from another. The most powerful tool for dissecting the secrets of a comet is spectroscopy. By passing the faint light from the comet's coma through an instrument called a spectrograph, astronomers can break it down into its constituent colors, creating a chemical fingerprint. This fingerprint reveals the specific molecules that are being released from the nucleus. The James Webb Space Telescope, with its powerful infrared spectrographs, was quickly tasked with observing 3I Atlas. Its findings were both surprising and familiar. The primary components detected in the coma were water vapor and carbon monoxide, two of the most common ices found in the comets of our own solar system. This discovery was profound. It suggests that the recipe for making comets might be remarkably universal across this region of the galaxy. The same basic building blocks of water and carbon-based molecules that were present in the protoplanetary disk that formed our own sun and its planets were also present in the system that gave birth to 3I Atlas. This implies that the fundamental ingredients for life as we know it, water and organic compounds, are likely not unique to our solar system, but are widespread throughout the galaxy, delivered to young planets by comets, just as they were to a young Earth. However, these early observations also presented a puzzle. While the ingredients were familiar, their proportions seemed slightly off. The ratio of carbon monoxide to water in 3I Atlas appeared to be different from that of most comets in our solar system. Furthermore, some early observations hinted that the comet became active much earlier than a typical solar system comet would, suggesting its ices might be more volatile or arranged differently within its nucleus. These were the first subtle clues that while the ingredients were the same, the oven in which 3I Atlas was baked, its home star system, may have had a very different environment than our own. These initial enigmas set the stage for the next, more intensive phase of observation, as the comet drew closer to the Sun and its activity began to reveal its true and perhaps unique character. As 3I Atlas continued its journey into the inner solar system through August and September of 2025, astronomers and amateur stargazers alike watched with anticipation. Comets are notoriously unpredictable. Some fizzle out, while others can erupt in spectacular displays of activity. With 3I Atlas, the show was just beginning, and it came with a surprising and beautiful twist. As the comet drew closer to the Sun, it began to brighten more rapidly than predicted, and more remarkably, it began to emit a distinct and ethereal green glow. This verdant hue is a well-known, though not always present, phenomenon in comets from our own solar system. It is not the color of the comet's nucleus itself, nor of the dust in its tail. The green light is a chemical ghost, a fleeting signal produced by the unique physics of the near vacuum of space. The source of this color is a simple, yet unstable molecule called dicarbon, which consists of two carbon atoms bonded together. This molecule is not found naturally on the surface of a comet's nucleus. Instead, it is created in the coma, the fuzzy atmosphere of gas surrounding the nucleus. The process begins as the sun's warmth heats the icy core of the comet, causing more complex organic molecules to sublimate and break apart. Under the harsh bath of the sun's ultraviolet radiation, these parent molecules are photodissociated, a technical term for being blasted apart by light. This process creates a variety of smaller, unstable fragments, including dicarbon. For a brief period, these dicarbon molecules exist in the dense inner coma of the comet. When sunlight strikes them, they absorb photons at a particular wavelength, and then re-emit that light, primarily in a specific shade of green. However, the life of a dicarbon molecule is incredibly short. It is itself highly susceptible to the same ultraviolet radiation that created it. Within just a couple of days, the sunlight destroys the dicarbon, breaking it apart into individual carbon atoms. This short lifespan is the reason why the green color is only ever seen in the head of the comet, its coma, and never extends into its long, streaming tail. By the time the gas and dust have been pushed away from the nucleus to form the tail, all the dicarbon has been destroyed. The sight of a green coma, therefore, is a direct visualization of the intense chemical reactions taking place in real time around the comet's core. The emergence of this green glow in 3I Atlas was a significant and reassuring observation for scientists. It demonstrated, in vivid color, that the fundamental chemistry taking place in this interstellar visitor was remarkably similar to that of our own comets. The presence of dicarbon confirmed that the nucleus, the 3I atlas, was rich in the same kind of carbon-based organic molecules that are found in comets from our own Oort cloud. These molecules are the fundamental building blocks of life as we know it, and their presence in an object from another star system is another powerful piece of evidence suggesting that these ingredients are common throughout the galaxy. For observers, the green glow transformed 3I Atlas from a faint, fuzzy patch of light into a truly beautiful celestial object. Astrophotographers around the world captured stunning images of the green-hued coma set against the backdrop of distant stars. These images, shared across the internet, brought the story of the interstellar visitor to a global audience, sparking a wave of public interest and wonder. The comet was no longer just a subject of scientific papers. It was a cosmic event, a shared moment of connection to the wider universe. This unexpected display of color, a result of familiar chemistry playing out on an alien stage, was a reminder that while the comet's origin was a deep and profound mystery, some of the physical laws that govern it are as universal as the light that makes it shine. The beautiful green glow of 3I Atlas was a stunning visual, a hint of the complex chemistry at play. But to truly understand the comet's nature, astronomers needed to look deeper, past the visible colors and into the fundamental ingredients being released from its icy heart. For this task, the James Webb Space Telescope was brought to bear. With its unparalleled sensitivity to infrared light, the light of heat and molecules, Webb is the most powerful tool humanity has ever built for dissecting the chemical makeup of faint, distant objects. Its observations of 3I Atlas would yield the most significant discovery about the comet yet. It was, in many ways, surprisingly and profoundly familiar. The Webb telescope's advanced spectrograph stared at the comet, capturing the faint infrared light from its coma and breaking it apart line by line into a chemical barcode. The results that came back were both a relief and a source of wonder. The dominant molecule detected was, as expected, water. The data showed the clear signature of water ice sublimating from the nucleus and water vapor filling the coma. The second most abundant molecules were carbon dioxide and carbon monoxide, also very common in the comets of our own solar system. Further analysis revealed traces of other familiar substances: methane, ammonia, and a variety of simple carbon-based organic molecules. The profound implication of this discovery cannot be overstated. The biggest news story was that there was no shocking news. The chemical recipe of 3I Atlas was remarkably similar to the comets that were born in our own solar system, particularly those that originate from the distant, icy reservoir known as the Oort cloud. It was like a geologist receiving a rock from a previously unexplored continent, only to find it was made of the same granite and quartz found in their own backyard. This suggests the existence of a universal recipe for making comets, at least in our corner of the Milky Way galaxy. This has staggering implications for our understanding of planetary formation and the potential for life elsewhere. Comets are the leftover building blocks of a solar system. They are cosmic time capsules, preserving the raw ingredients that were present in the swirling disk of gas and dust that formed around a young star. The fact that 3I Atlas is made of the same materials as our own comets strongly suggests that other star systems are built from a similar chemical toolkit. It means that the fundamental ingredients for life as we know it, water and complex organic compounds, are likely not a cosmic rarity. They are probably widespread throughout the galaxy, delivered to newly forming rocky planets by cometary impacts, just as they were delivered to a young Earth billions of years ago. Yet amidst this surprising familiarity, subtle and important differences began to emerge. While the ingredients were the same, the proportions were slightly different. The ratio of carbon dioxide to water ice in 3I Atlas was found to be unusually high, one of the highest ever recorded in a comet. This small but significant detail is a crucial clue about the comet's mysterious home. The amount of carbon dioxide that can freeze onto a comet's nucleus depends on the temperature of the region where it formed. This finding may indicate that 3I Atlas formed in a particularly cold region of its parent solar system, or perhaps that the system itself was unusually rich in carbon. These subtle chemical variations are like a local accent in its otherwise universal language, the only clues we have to the specific conditions of its lost home. Despite knowing what it is made of with increasing precision, we still do not know where exactly it came from. Its trajectory points back towards the galactic core, but its journey has been so long, lasting for millions of years, that its parent star has long since moved from its original position. The galaxy is not a static map. The stars are in constant motion. Tracing the comet's path back to a single point of origin is an impossible task. It is, and will almost certainly remain, a cosmic orphan. Its familiar composition tells us that our solar system is not unique, but its precise origin remains one of its most tantalizing secrets. The chemical composition of 3I Atlas, so familiar to astronomers, is the fuel for its magnificent transformation. As the comet continues its plunge towards the Sun through September of 2025, it is moving from the cold, dark outer regions of our solar system into a domain of increasingly intense solar radiation. This growing warmth is the engine of cometary activity, a process that is now converting 3I Atlas from a quiet traveler into a dynamic and spectacular celestial object, complete with the feature that most defines a comet, a long, streaming tail. The process begins at the nucleus, the comet's solid core of ice and rock. As sunlight strikes the surface, the ice does not melt into a liquid. In the vacuum of space, it sublimates, turning directly into a gas. This expanding gas erupts from the surface in powerful jets, carrying with it vast quantities of dust and debris that were once trapped within the ice. This mixture of gas and dust forms the cloud around the nucleus, known as the coma, which has been steadily growing in size and brightness. But the forces of the sun do not stop there. They act upon this newly formed atmosphere, pushing and sculpting it to create the comet's magnificent tails. As 3I Atlas develops, observers are able to clearly distinguish two separate tails, each formed by a different process and made of different materials. The first is the dust tail. This is composed of the microscopic grains of rock and dust that were carried away from the nucleus by the erupting gas. These particles are relatively heavy, and they are gently pushed away from the comet by the pressure of sunlight itself. This faint but constant pressure, the force exerted by countless photons striking the dust grains, nudges them away from the sun. The dust tail is often broad, diffuse, and slightly curved, as the heavier particles tend to lag behind the comet in its orbital path. It shines with a pale, yellowish-white light, the simple reflection of sunlight from the trillions of tiny particles. The second tail is the ion tail, also known as the gas tail. It is a much more dramatic and ethereal structure. The gas that sublimates from the nucleus, molecules like carbon monoxide and water vapor, is directly exposed to the sun's harsh ultraviolet radiation. This radiation is energetic enough to strip electrons from the gas molecules, giving them an electrical charge and turning them into ions. These newly created ions are then captured and violently swept away by the solar wind, a constant stream of charged particles flowing out from the sun at hundreds of kilometers per second. Because the solar wind moves so fast, it forces the ion tail to point almost directly away from the sun, regardless of the comet's direction of travel. This tail often glows with a distinct bluish light, a result of the ions fluorescing as they are energized by the solar wind. In the most recent observations of 3I Atlas, both tails are becoming more prominent with each passing week. The broad, curved dust tail is becoming easier to photograph, while the thin, straight ion tail now stretches for over 1,000,000 kilometers through space. This increasing activity is a sign that the comet is healthy and active, but it also introduces an element of unpredictability. As the heating intensifies, the pressure building up inside the nucleus can cause sudden outbursts of gas and dust, making the comet brighten dramatically overnight. In more extreme cases, these stresses can cause the entire nucleus to fracture and break apart. Astronomers are monitoring 3I Atlas with a watchful eye, knowing that as it approaches its closest point to the Sun, the perihelion, its beautiful display could become even more spectacular, or it could signal the beginning of the comet's final dramatic dissolution. Every orbit, whether it is the near circular path of a planet or the long looping journey of a comet, has a single point of maximum drama. It is the moment of closest approach to the Sun, a point known as the perihelion. For a comet, this is the climax of its voyage through the solar system. It is the moment of most intense heating, greatest speed, and maximum stress, a trial by fire that can transform the object, reveal its deepest secrets, or destroy it completely. For 3I Atlas, this critical passage is predicted to occur in late October of 2025, and the astronomical community is preparing to watch with rapt attention. The trajectory of 3I Atlas has been calculated with incredible precision. Its path will carry it safely through the solar system, well outside the orbit of Earth. Its perihelion will occur on the 29th of October, at which point it will be approximately 210 million kilometers from the Sun. This is a safe distance, further from the Sun than the Earth is, placing it roughly between the orbits of our own planet and Mars. As it swings around the Sun, its speed will be immense, accelerated by our star's powerful gravity to a velocity of over 200,000 kilometers per hour. This incredible speed is a stark reminder of its interstellar origin, a momentum carried with it from the vast emptiness between the stars. The perihelion passage is of paramount importance to scientists because it is the period of maximum activity. The intense solar radiation will heat the comet's nucleus to its highest temperature, causing ices buried deep within its core to sublimate and erupt to the surface. These jets of gas will carry material that has been frozen and preserved for billions of years, material from the very heart of the comet. By analyzing the light from the coma during this period, spectrographs like those on the James Webb Space Telescope can get their clearest look yet at the primordial composition of this interstellar visitor, potentially identifying new and more complex molecules that are not visible when the comet is colder and less active. This period of intense activity also provides the best opportunity to study the solid nucleus itself. Often, a comet's core is obscured by the bright, fuzzy cloud of its own coma. But during a close pass to the Sun, the violent outgassing can sometimes temporarily clear pockets of gas and dust, giving powerful telescopes like Hubble a fleeting chance to glimpse the surface beneath. Scientists will be hoping to capture images that can reveal the nucleus's shape, its rotation, and any distinct surface features like fissures or craters. Furthermore, the perihelion is the ultimate stress test. The combination of intense solar heating and the immense gravitational forces from the Sun can put an enormous strain on the comet's fragile, icy structure. It is not uncommon for comets to fracture or even completely disintegrate during their closest approach. While this would mark the end of 3I Atlas as a single object, it would be a spectacular scientific opportunity. A breakup event would expose the comet's pristine interior, allowing scientists to study its internal structure and composition in a way that would otherwise be impossible. For this reason, observatories around the world are coordinating a massive, continuous observation campaign. As the comet passes through perihelion, it will be monitored 24 hours a day, with telescopes in different time zones handing off the watch to one another. Every change in brightness, every new jet of gas, every subtle shift in its path will be recorded and analyzed. This is the moment when the visitor from another star, under the intense interrogation of our sun, will be forced to give up its most profound secrets. The intense observation of 3I Atlas as it passes perihelion is not a story confined to Earth. While ground-based telescopes and orbiting observatories like Hubble and Webb provide a wealth of data, their perspective is fundamentally limited. They are all, in a cosmic sense, in the same place, looking at the comet from the same general direction. To truly understand a complex, three-dimensional object like a comet, with its vast and tenuous tails stretching for millions of kilometers, scientists need to see it from multiple angles. For this reason, a coordinated campaign has begun, enlisting a fleet of robotic explorers scattered across the inner solar system to turn their own electronic eyes towards the interstellar visitor. This multi-probe campaign transforms the observation from a simple viewing into a solar system-wide investigation. The fleet of spacecraft currently orbiting Mars, for example, offers a perfect alternative vantage point. Missions like NASA's MAVEN orbiter and ESA's Mars Express are equipped with sophisticated instruments designed to study the Martian atmosphere. As 3I Atlas makes a relatively close approach to the red planet, these instruments can be retasked. Their ultraviolet spectrographs, for instance, are perfectly suited to studying the composition of the comet's coma, providing data that can be compared with that from the Webb telescope to build a more complete chemical profile. Observing from the orbit of Mars also provides a different line of sight, allowing scientists to build a more accurate, three-dimensional model of the jets of gas erupting from the comet's nucleus. An even more tantalizing opportunity comes from the spacecraft designed to study the Sun itself. Probes like NASA's Parker Solar Probe and ESA's Solar Orbiter are built to withstand the intense environment near our star and are equipped with instruments designed to measure the solar wind and the Sun's magnetic field. These probes are in a unique position to conduct what is known as in situ science. Instead of just looking at the comet from afar, they can physically pass through its faint, extended tail. As 3I Atlas rounds the Sun, its immense ion tail, pushed away by the solar wind, will sweep across a vast swath of the inner solar system. Mission planners at both NASA and ESA are working to align their solar probes to cross this path. If successful, the Parker Solar Probe could fly directly through the ion tail. Its instruments, designed to taste the solar wind, would be able to directly sample the particles from another star system. It would be able to measure the tail's magnetic field, its density, and its composition in a way that is impossible from hundreds of millions of kilometers away. This would be a remarkable feat of celestial navigation, a fleeting encounter that would provide an unprecedented level of detail about the interaction between an interstellar object and our Sun. Coordinating such a campaign is a monumental effort. It requires reprogramming multi-billion-dollar spacecraft, sometimes asking them to perform maneuvers or point their instruments in ways their original mission designers never intended. It involves teams of scientists and engineers from around the world sharing data in real time, piecing together observations taken millions of kilometers apart to form a single, coherent picture. This global, multi-planetary effort underscores the scientific importance of this rare visitor. The data gathered will not just be about one comet. It will be a holistic snapshot of how an object from the interstellar medium behaves when it passes through a star system, a complex dance between the comet, the Sun, and the solar wind, observed from every possible angle. The frantic, Coordinated climax of the perihelion passage marks the peak of our encounter with 3I Atlas. Having survived its trial by fire, the comet swings around the sun and begins the second half of its journey, the long, quiet, and irreversible voyage back out into the interstellar void. For the astronomers who have been tracking its every move, this departure phase is a race against the clock. The visitor is leaving, and the window of opportunity to study it is closing with each passing day. The farewell to 3I Atlas is a gradual one, a slow fade into the distance that underscores the fleeting nature of these celestial encounters. Having reached its maximum velocity as it whipped around the sun, the comet now begins to slow slightly as it climbs back out of our star's gravity well. It is like a ball that has rolled down one hill and is now traveling up another, much gentler one. The sun's gravity, though not strong enough to capture it, still exerts its influence, gradually bleeding away a small fraction of the comet's immense kinetic energy. But it will never slow down enough to be trapped. Its momentum is too great, and its path is forever pointed towards the stars. Eventually, millions of kilometers away, it will escape the last vestiges of our sun's influence and resume its steady cruising speed through the galaxy. As the comet recedes from the sun, the two primary factors that make it a spectacular object for study begin to diminish. The first is its activity. Moving back into the cold outer solar system, the intense solar heating that drove its beautiful green coma and long tails subsides. The sublimation of its surface ices slows to a trickle and will eventually stop altogether. As this internal engine shuts down, the coma will shrink and fade, and the tails will dissipate into space. The comet's dramatic gaseous shroud will vanish, and it will slowly revert to what it was for millions of years in the interstellar darkness, a simple, inert nucleus of ice and rock. The second factor is the simple, unforgiving geometry of distance. As 3I Atlas moves away from both the sun and the Earth, its apparent brightness plummets. The intensity of light follows an inverse square law. For every time the comet doubles its distance from us, it becomes 4 times fainter. This rapid dimming means that the group of telescopes capable of studying it begins to shrink. First, amateur astronomers and those with smaller instruments will lose sight of it. Then, one by one, the larger ground-based observatories will find it too faint to gather meaningful data. In this final phase of the observation campaign, the torch is passed to the giants. For as long as possible, the world's most powerful telescopes, like the Vera C. Rubin Observatory in Chile, will continue to track the comet's faint motion. Their primary goal is to gather every last data point on its position, allowing for the most precise possible calculation of its departure trajectory. This will help future astronomers know exactly where to look for any subtle gravitational influences it may have had on our own outer solar system. Eventually, the comet will become too faint even for these terrestrial giants. The final goodbye will belong to the space telescopes, Hubble and Webb, who will follow the faint point of light until it becomes utterly indistinguishable from the billions of other distant stars and galaxies. At some point in the coming year or two, a final image will be taken, a last faint photon will be collected, and 3I Atlas will vanish from our view forever. Its silent, lonely journey back into the dark is a powerful reminder that while the galaxy may be full of these messengers, each encounter is a unique and precious moment in time. As 3I Atlas fades from our telescopes, its lasting legacy begins to come into focus. The specific data gathered from its nucleus and coma are invaluable, but its greatest contribution to science may be its very existence. The arrival of a third confirmed interstellar object in such a short span of time has permanently shattered our old notions of the emptiness of space. It is a powerful statistical statement, one that has forced astronomers to radically revise their understanding of the galaxy and to accept that our solar system is not an isolated island, but a coastline on a vast and busy cosmic ocean. When the first visitor, Oumuamua, was detected in 2017, it was treated as a profound anomaly. The scientific consensus at the time was that such encounters were extraordinarily rare, and that we were incredibly lucky to have spotted one in our lifetime. Some early estimates suggested we might see one such object pass through our system per century. But then just 2 years later, 2I Gorisov arrived, a discovery that strained the definition of coincidence. It was a clear sign that our initial estimates were likely wrong. The arrival of 3I Atlas in 2025 has solidified this new reality, moving the needle from rare coincidence to expected occurrence. The anomaly is becoming the norm. The most useful way to understand this is through the iceberg analogy. Our current sky surveys, as powerful as they are like a small fishing net cast into an unimaginably large ocean. For decades, we caught nothing. Now, in just a few years of looking more closely, we have caught 3. The unmistakable implication is that for every visitor we are able to detect, there are thousands, perhaps millions that pass by unseen, too small, too dark, or too far away for our current technology to spot. The objects we find are merely the most visible tips of a colossal, invisible iceberg of interstellar material drifting through our solar system. This has led astronomers to recalculate the population density of these wandering objects. While the numbers are still debated and refined with each new piece of data, the current models are staggering. They suggest that at any given moment, there could be thousands of Oumuamua objects passing within the orbit of Neptune. The space within our own solar system is likely teeming with these silent travelers from other stars. Extrapolated to the galaxy as a whole, it is estimated that there may be more interstellar comets and asteroids wandering through the void than there are stars in the Milky Way. This vast, unseen population of objects is the lost diaspora of planetary formation. In the early, chaotic days of a new star system, as giant planets form and migrate, their immense gravity acts as a cosmic slingshot, ejecting trillions of smaller, icy, and rocky bodies from their home system out into interstellar space. Our own solar system, in its youth, was no different. We likely contributed countless comets from our own Oort cloud to this galactic reservoir. The galaxy, therefore, is not a collection of isolated star systems separated by sterile emptiness. It is a dynamic, interconnected ecosystem, constantly exchanging material. The discovery of 3I Atlas is another confirmation that we are constantly moving through the ghostly remnants of other worlds, a silent, invisible traffic of cosmic driftwood. The message of this third visitor is clear. We are not alone, not because of a signal or a spacecraft, but because the very substance of other star systems is all around us, all the time. The discovery that interstellar visitors like 3I Atlas are a common feature of our galaxy is a revelation. It means that nature provides a steady stream of free samples from distant star systems, delivering them directly to our doorstep. Each of these objects is a pristine time capsule, a frozen, unaltered remnant of the specific protoplanetary disk in which it was born. To study one of these comets is to conduct an archaeological dig on the formation of another world, and by doing so, we gain an unprecedented window into the diversity of solar systems across the galaxy. The story that 3I Atlas tells begins with its remarkable familiarity. As we have seen, its primary components, water, carbon dioxide, and carbon monoxide, are the very same building blocks that make up the comets of our own solar system. This suggests that the vast clouds of gas and dust from which new stars and planets are born share a relatively consistent chemistry, at least in our region of the Milky Way. This is a crucial finding, as it implies that the basic ingredients for worlds like our own are not a cosmic fluke, but a galactic standard. However, it is the subtle differences in its composition that provide the most valuable clues. As astronomers look closer, they see that while the ingredients are the same, the recipe is slightly different. The most telling of these differences is the unusually high concentration of carbon monoxide ice found in 3I Atlas. This detail allows scientists to begin to paint a picture of the specific environment in which the comet formed, millions or billions of years ago. In a young, developing solar system, different types of ices can only form at specific distances from the parent star, a concept known as the frost line or snow line. Water ice, for example, can form relatively close to a young star, but carbon monoxide is a much more volatile substance. It can only freeze into a solid ice at extremely low temperatures. This means it has a frost line that is much, much further out from the star. The fact that 3I Atlas is so rich in carbon monoxide strongly suggests that it was born in the frigid, distant outer reaches of its home solar system, a region likely far colder and more distant from its star than our own Kuiper belt is from our sun. This single chemical measurement allows us to infer a key detail about the architecture of an alien solar system we will never see. It gives us a glimpse into the temperature gradient and structure of its primordial disk. By comparing this new data point with our previous two visitors, a more complex picture of galactic diversity begins to emerge. The first visitor, 1I Oumuamua, was a bizarre, rocky, and inert object, completely unlike a typical comet. Some theories suggest it may have been a nitrogen iceberg, chipped off a Pluto-like exoplanet, or perhaps a fragment from a larger body that was torn apart by its star. It may represent a class of objects from the inner part of a solar system. The second visitor, 2I Borisov, was much more familiar, behaving like a classic comet, though it also had a very high concentration of carbon monoxide. Our third visitor, 3I Atlas, continues this trend. It is clearly a comet, but with its own distinct chemical accent, one that hints at an origin in an extremely cold, carbon monoxide-rich environment. What this tells us is that while the basic chemistry may be consistent, the specific conditions of planet formation vary greatly from one system to another. By collecting and comparing the fingerprints of more and more of these interstellar messengers, we can move beyond studying our own solar system in isolation. We can begin to build a true galactic census, understanding the full range and diversity of planetary systems that the Milky Way has to offer. Each visitor is a unique and precious data point, a single sentence in a long and complex story about the birth of worlds. The study of 3I Atlas from afar, using the powerful telescopes of Earth and our robotic probes, has provided an unprecedented glimpse into a piece of another solar system. We have learned its size, its color, and its chemical composition, but remote observation, as powerful as it is, will always have its limits. It is like trying to understand a new and exotic land by looking at it through a pair of binoculars from a distant shore. To truly know it, to understand its texture, its substance, and its secrets, you must go there. This desire has given rise to one of the most ambitious and challenging goals in modern space exploration: to design a mission that can physically intercept one of these interstellar visitors during its fleeting passage through our system. The challenge of such a mission is almost impossible to overstate, and it is defined by the tyranny of speed and time. Interstellar objects, by their very nature, are moving at incredible velocities relative to our Sun. They are not on lazy, predictable orbits like the planets. They are cosmic bullets, and we only see them as they are whizzing past. By the time we discover an object like 3I Atlas, confirm its interstellar origin, and calculate its trajectory, it is often already at its closest point to us and is beginning its journey back out into the void. The window of opportunity is terrifyingly short. Our current approach to space exploration involves years, sometimes decades, of planning and construction for a single mission. We simply do not have the ability to design, build, and launch a spacecraft from scratch in the few months we have to catch a departing target. The story of the first interstellar visitor, 1I Oumuamua, is a perfect and painful illustration of this problem. By the time the scientific community fully grasped the profound significance of what they were seeing, the object was already heading away from us at high speed, well beyond the reach of any rocket we could launch. It was a historic opportunity, a chance to get a close-up look at an object from another star. That was missed simply because we were not prepared. This missed opportunity served as a powerful wake-up call, forcing a fundamental rethinking of how we approach the exploration of these transient targets. If we cannot chase them down from a standing start, then we must already be in position, waiting to give chase. This is the new strategy, a form of cosmic ambush. The European Space Agency is already developing a mission based on this very concept, a probe aptly named the Comet Interceptor. The idea is revolutionary in its patience. The Comet Interceptor spacecraft will be launched, not to a specific destination, but to a stable gravitational point in space. The Sun-Earth Lagrange Point 2, located about 1.5 million kilometers from Earth. There, it will enter a parking orbit, a state of cosmic hibernation, fully fueled and with its instruments ready. It will simply wait. Its mission is to wait for a target of opportunity to be discovered by the next generation of powerful sky surveys. The ideal target would be a pristine comet from our own Oort cloud, making its very first journey towards the Sun. But the ultimate prize, the mission's dream target, would be the next interstellar object to be detected on an inbound trajectory. When that object is found and its path is confirmed, the Comet Interceptor will awaken. With its target locked in, it will fire its engines and begin a multi-year, perfectly calculated chase, leaving its parking spot to intercept the visitor as it journeys through the solar system. A successful interception would be one of the greatest achievements in the history of space exploration. A close flyby would allow a spacecraft to do things that are impossible from Earth. High-resolution cameras would capture the first detailed images of the surface of an object from another star system, revealing its geology and texture. A mass spectrometer could fly directly through the coma, tasting the gas and dust to provide a definitive chemical analysis, free from the ambiguities of remote spectroscopy. Instruments could measure the density of the nucleus, its temperature, and search for a magnetic field. We would no longer be guessing about the nature of these objects. We would be measuring them directly. The discovery of 3I Atlas has only intensified the desire to make such a mission a reality. While it is too late for us to send a welcoming party to this particular visitor, its passage serves as a powerful reminder that others are coming, and that next time we must be ready and waiting. The fleeting visit of 3I Atlas highlights both a tremendous opportunity and a significant challenge. While our science has become remarkably adept at characterizing these interstellar visitors once they are in our midst, our ability to intercept one has been hampered by a single critical factor: a lack of advance warning. The current generation of sky surveys, as successful as they have been, typically only find these objects when they are already deep inside our solar system, moving at their fastest and already on their way out. To move from the passive act of observing these messengers to the active one of visiting them requires a new strategy and a new generation of eyes on the sky, capable of spotting these faint travelers long before they arrive. The discovery of I Oumuamua and 2I Borisov, and now 3I Atlas, was made possible by automated sky surveys like Pan-STARRS and Atlas. Their primary mission is to repeatedly scan the sky, taking pictures and having computers compare them to find anything that has moved or changed. While they are powerful, they can only see the brightest or closest objects. We are, in effect, only seeing the visitors that skin right past our front porch. To find the ones that are still far down the street, we need a much bigger and more sensitive tool. That tool is now coming online, and it promises to revolutionize this hunt. High in the Chilean Andes, on the mountain of Cerro Pachon, a new observatory is beginning its mission. It is the Vera C. Rubin Observatory, and its 10-year mission is called the Legacy Survey of Space and Time, or LSST. The scale of this project is breathtaking. It combines a massive 8.4-meter mirror with the largest digital camera ever constructed, a device of 3.2 gigapixels. Its mission is not to stare intently at one small patch of the sky, but to do something unprecedented, to survey the entire visible southern sky every few nights with incredible depth and precision. In essence, the Rubin Observatory will create the first high-definition motion picture of our universe. This capability is a complete game-changer for the hunt for interstellar objects. The observatory's immense light-gathering power will allow it to detect objects that are much smaller, much darker, and much farther away than anything our current surveys can see. This means that we will be able to spot the next interstellar visitor, not months before its closest approach, but potentially years in advance, when it is still crossing the orbit of Saturn or even Neptune. It will see them coming when they are still moving relatively slowly, giving us the one thing we have desperately needed: time. With several years of advance warning, the entire dynamic of our response changes. A mission like the European Space Agency's Comet Interceptor would no longer be a hypothetical dream, but a practical reality. With the incoming object's trajectory calculated with high precision years ahead of its arrival, mission planners would have ample time to plot the most efficient course for their waiting spacecraft. The interceptor could be directed to a specific point in the solar system, arriving just in time to fly alongside the visitor, studying it in detail for weeks or even months. The Rubin Observatory acts as the perfect cosmic lookout, spotting the intruders from afar, while the Comet Interceptor acts as the rapid response vessel ready to engage. Astronomers predict that once the Rubin Observatory begins its full survey, the floodgates will open. The discovery of interstellar objects will be transformed from a rare, celebrated event into a routine, perhaps weekly occurrence. We will move from a collection of 3 precious data points to a rich catalog of hundreds and perhaps thousands of these objects. We will be able to see the full diversity of this interstellar population, from icy comets to rocky asteroids, and perhaps even stranger objects that we cannot yet imagine. The era of accidental discovery is drawing to a close. We are now entering the age of the systematic hunt, proactively scanning the cosmos to find the next messengers before they find us, and preparing ourselves to finally meet one face to face. The relentless hunt for interstellar visitors, powered by new technologies like the Vera C. Rubin Observatory, promises to fill our catalogs with a wealth of new data. We will learn the intricate details of their chemistry, the range of their sizes, and the frequency of their passage. But the story of 3I Atlas and its kin transcends the realm of pure scientific curiosity. The discovery of these objects is not just an astronomical event, it is a philosophical one. It forces us to confront our place in the universe in a way that is both humbling and profoundly exciting, challenging our old assumptions and opening our minds to new, incredible possibilities. For centuries, science has been guided by the Copernican principle, the idea that we are not special. Our planet is not the center of the solar system, our sun is not the center of the galaxy, and our galaxy is not the center of the universe. We are, in a cosmic sense, average. The discovery of interstellar comets like 2I Borisov and 3I Atlas provides the first tangible chemical proof of this principle beyond our own system. The fact that these visitors are made of the same fundamental building blocks as our own comets, the same water, the same carbon compounds, is a powerful confirmation that our solar system is not a unique creation. We are made of standard, galactic-grade material. The recipe that created Earth is likely not a secret one. This realization has profound implications for the search for life. If the raw ingredients for life, water and organic molecules, are not unique to our corner of the cosmos, but are instead being constantly mixed and distributed throughout the galaxy by a vast population of wandering comets, then the potential number of habitable worlds skyrockets. These interstellar messengers tell us that countless other nascent planets, orbiting countless other stars, were likely showered with the same life-giving ingredients that our own Earth received in its youth. The discoveries do not prove that life exists elsewhere, but they strongly suggest that the conditions for it to begin are not rare, but common. This new understanding of a galaxy teeming with wandering comets has also breathed new life into a fascinating and speculative hypothesis known as panspermia. This is the idea that life itself, not just its ingredients, could travel between the stars. The theory suggests that microscopic organisms, hardy extremophiles capable of surviving the vacuum and radiation of space, could be ejected from their homeworld by an asteroid impact and become trapped inside a comet. After a journey of millions of years in a deep, frozen hibernation, that comet could then crash into a new, fertile world, seeding it with life. While it remains a fringe theory with no direct evidence, the confirmation that a viable delivery system exists on a massive galactic scale makes the idea more plausible than ever before. Objects like 3I Atlas are proof that the delivery system is real and operational. Ultimately, these visitors change our perception of the galaxy itself. We are accustomed to thinking of it as a majestic but static collection of isolated islands of light, separated by an impassable, sterile void. This is wrong. The constant traffic of interstellar objects reveals the galaxy to be a single, interconnected ecosystem. Star systems are not isolated. They are constantly shedding material, and that material, the pollen of other worlds, is constantly drifting through our own backyard. For all of human history, our story has been confined to the Earth. The arrival of these objects is the first time we have made physical contact, however distant, with the story of other stars. They are a humbling reminder that our solar system is just one chapter in a galactic saga of unimaginable age and scale, and that countless worlds have likely formed, lived, and died long before our own. The legacy of 3I Atlas, therefore, is a philosophical one. It solidifies our place as an ordinary part of a grand, interconnected cosmos, a universe far more dynamic and potentially far more alive than we ever knew. The passage of 3I Atlas through our solar system is a fleeting event. Soon, it will grow too faint to be seen by even our most powerful telescopes, and it will recede back into the interstellar darkness from which it came, never to be seen again. But even as it vanishes from sight, it leaves behind a profound and permanent legacy. The discovery and study of this third interstellar visitor, along with its predecessors, 1I Oumuamua and 2I Borisov, has fundamentally altered our perception of the universe and our place within it. Their legacy is not just a collection of data, but a new awareness, a new set of aspirations, and a new chapter in the human story. The first great legacy is the confirmation of abundance. These objects have taught us that the vast void between the stars is not empty. The galaxy is filled with a constant, silent traffic of wandering comets and asteroids, the lost children of other star systems. We now understand that our solar system is not an isolated island, but a part of a dynamic, interconnected galactic ecosystem that is constantly exchanging material. The discovery of 3I Atlas has solidified this view, transforming our understanding of the galaxy into a place of surprising richness and activity. The second legacy is that of familiarity. The detailed analysis of 3I Atlas has shown us that the fundamental chemistry of other star systems is remarkably similar to our own. This visitor, born in a different corner of the galaxy, is made of the same water and the same carbon-based organic molecules that make up our own comets and ultimately ourselves. This is a powerful reinforcement of the Copernican principle, the idea that we are not a cosmic exception, but a product of a universal set of rules. It is a humbling and deeply encouraging finding, suggesting that the basic building blocks for life are not rare, but are a common galactic standard, making the universe a more promising place in our search for life beyond Earth. Finally, there is the legacy of aspiration. These fleeting visits have inspired a new and proactive era of space exploration. They have exposed the limitations of our current ability to react to sudden discoveries, and have become the driving force behind the next generation of technology. They are the reason for building powerful new sky surveys like the Vera C. Rubin Observatory, which will hunt for these objects systematically. And they are the reason for designing innovative new missions like the Comet Interceptor, which will lie in wait, ready to give chase to the next visitor that comes our way. These messengers have given us a new, tangible, and ambitious goal: to one day touch a piece of another star system. The journey of 3I Atlas comes to a close, but the journey of our understanding has just begun. These objects connect us to the wider universe in a physical and profound way. They are a tangible link to the stories of other stars, a humbling reminder that our own story is just one part of a much larger, more ancient cosmic narrative. Even as this particular messenger disappears back into the night, we can take comfort in the knowledge that it is not the last. Others are already on their way, a constant, silent stream of travelers from the stars, and we will be ready and waiting to learn the secrets that they carry. The journey continues, always calmly, always at the rhythm of the universe.